Hi and welcome to the SEG AAPG International Meeting for Applied Geoscience and Energy. On behalf of Christopher and myself, I present to you Resolving Sedimentary Features in a Lower Miocene Clastic Reservoir, Jeanerette Field, Louisiana. The abstract, it's a lot to read, but basically I'll give you a little synopsis here. In 2004, a well was drilled, which penetrated two very small reservoirs, very thin gas-charged reservoirs. The lower reservoir, which was the thinner of the two, produced for over a year, and then eventually they shut it down. And during the recompletion for the upper reservoir, they started losing tools in the hole. And during the fishing operations, there was a collapse in the casing, so the well was eventually abandoned. A second well was drilled up dip, try to target the same anomaly that they had success in the first well, but it ended up being a dry hole. And in this study, we used seismic data and well data to determine why the second well missed the target. Basically, the resulting gamma ray result, which is very high frequency, shows a clear compartmentalization within the reservoir. And the increased resolution also has enabled the mapping of lateral discontinuity of the sand, enhanced fault expressions, and stratigraphic details that were not visible using the conventional seismic information by itself. A little bit about the geology. It's lower Miocene. The reservoir is of lower Miocene age and is defined as a sequence of interbedded erratic sands and deep marine shales. There's a lot of faults in this area. It's high pressure, very deep. It's difficult to image, which explains the low resolution of the seismic. Depositional environment is proximal and distal deltaic to slope, 40 feet of gas-charged sand, 12 to 20% porosity. We have the second well also, but there is no log information below 11,500 feet. St. Mary Parish, Louisiana, and you can see it here on the map. During the recompletion, the operator lost the tools in the hole. Fishing operations resulted in a collapse of the casing. You can see they started producing in April of 2005. You can see here million cubic feet per day. They reached about 10,000 MCF. I want a couple points here. Just before November 2006, they stopped production, and that's when during the recompletion they started having the issues. This is the primary well logs. You can see the top and the base of the reservoir here on the gamma ray. And as you can see, there's some interbedded shales, or so I don't consider it's not a very clean reservoir. It's kind of a dirty reservoir. You have the upkick in the resistivity. P wave response is virtually nothing. So the density does lower because of the presence of the gas. So this is a 3D view of the full stack seismic, and you can see the well trajectory here. It's it's highly deviated well, top and base of reservoir. And this is the anomaly that they were shooting for. And with a little interpretation here, we have a couple of faults here, growth fault here, and the salt dome below, which is one of the culprits for the difficult geologic environment, we'll say. All right, prior to our study, we took the offset gathers and we cleaned them up. We had a few targets or a few aims in our conditioning to reduce the noise and the removal of internal multiples. Data needed to be aligned. That was one of the issues, is that when you went from near to far, you had a lot of kind of displacements in the events. And obviously we wanted to increase the signal to noise ratio, but that's easier said than done when you're conditioning seismic data. Radon, RMO, Van Gogh filter, and you apply the mutes, generate partial stacks. We did near, mid, and far. Things about 4 to 14, 14 to 24, and 24 to 34 degrees. And finally, the machine learning inversion, if you will. It's not really an inversion. I guess it is, but it's not the inversion that we're all used to. But yeah, you get your high definition gamma ray. This is a comparison. Well, first we're going to compare the before and after seismic conditioning. This is before. These are the raw gathers prior to anything. Well data is at this middle gather. This is pretty much the zone where the reservoir is, right about here actually. After conditioning, we see a pretty big improvement. Yep, generated the stacks, and these are now the inputs and outputs to our machine learning workflow. So we have our near, mid, and far, so no more wavelets, which is good. Hybrid model, it incorporates both low frequencies of the property that you're trying to solve for, and you also have seismic. And I'm not going to get into too much detail here, but this is what I call the hybrid model. And you have your hybrid model and your angle stacks, feed that to the machine learning ensemble algorithm, and then you get your property volume. In this situation, we're using, we're shooting for gamma ray. I have tried with only full stack, just like one full stack seismic input, and the results are nowhere near as good. So I can confidently say that pre-stack seismic is a requirement in this workflow. And another thing, this can be carried out in the depth or time domain. Any QI geophysicist will tell you how nice it is to stay in the depth domain if you have your depth data. You don't have to tie wells. You don't have to convert from depth to time and then back to depth. So it is a big plus to be able to work in the depth domain. But not all the time the depth gathers or the depth stacks are available. So I've run into many times where there's only time domain data, but I used to really love time domain data because I always did simultaneous inversion, which requires time domain data. Anyway, ensemble machine learning algorithm. So ensemble methods, it's a technique that combines several base models in order to produce one optimal predictive model. So you can see it here. You've got multiple predictions for these trees, and then your ensemble machine learning final solution is kind of like a mean of all the different predictions. This technology, in many cases, yields a lower error than other machine learning algorithms, and it's less prone to overfitting. And yeah, so I've tried several machine learning algorithms to predict gamma ray, and I found that ensemble methods are the best from my experience. So let's go to the results. So on the left hand side, we see it's a random line that goes through, kind of like targets the bottom of the trajectory. It's very highly deviated, so that's why you can see these little kind of like jumps. This is the reservoir, so this is the gamma ray log here, and it has a 140 hertz filter applied, so you can see the low gamma ray here. This is our reservoir. And the reason the reason why I chose 140 hertz is because that was my target in the machine learning algorithm. So that was what I used as my target frequency. On the right hand side, we have our high definition gamma ray result, and you can see it's a very nice match with the well. But that being said, there's no validation well, which is not good for machine learning studies. But when you extract the data at a well and use that information to build your machine learning model, I mean, if you're going to have any chance of success, it better look something like this. It better be spot on. So I've tried this on another data set, and I had a second well, and on that one I got very, very good result, as you would expect at the well that was used in the machine learning model building. But that other project, I was able to validate it and make a blind well test. This one, I don't have that, unfortunately. There are logs on the other well, which we're going to get to soon, but they stop way up here. I think they go down to like 11,500 feet. So this is the salt over here again. So now let's compare between the seismic and the gamma ray result. And you can see the reservoir here. So it's a nice low gamma ray. But you can see a lot of other things here that could be potential reservoirs. This is kind of like channel sands here. I had the impression from my geologic information acquisition in this field I think that this is a good result. This looks like what you would expect in a deltaic environment, and in terms of like having channel sands. And I've circled all the ones that are low gamma ray, and then kind of compare them on the seismic. You can see if this is true, you do not have any clear indication of these being zones of interest based only on the seismic. So now this is the second well that was drilled, and then you can see why they did it. So you have, this is your target. They get some production, enough to make them want to do it again. And then here you have what they believe is the same sand based on the seismic response, which is also a strong peak. And now let's look at the same thing on the gamma ray. Here you can see there's a fault right about here, and it's kind of like a very difficult fault to detect. You can't really see it on the seismic. I guess maybe someone could argue that there's a fault here, but here you can see more clearly that there's a fault. And this is also shows that this is an isolated sand. It's compartmentalized. It has no connection to the second well, which was a dry hole, like I mentioned. So I'm not sure if they were shooting for, let's look at it here, maybe they were shooting for this and they continued to drill. But I'm very happy to see this, because according to the gamma ray, if they had this information, I think they would have potentially thought twice about putting their well where they put it. Maybe they would have placed it a little bit further up dip. So now a time slice comparison. This is the seismic. You have your primary well here and your secondary well here. This time slice does not really apply over here because this is more shallow. But what I want to show is a comparison between what you see from above in terms of seismic amplitudes versus the gamma ray result. And you can see here, this is your low gamma ray reservoir. So this time slice is right smack through the reservoir zone. And I thought this was very interesting. You see this little channel sand here. You also see some more stuff over here, some more stuff over here. But I really like this. Whenever I generated this slice, I thought to myself, hey, you gotta show this. Conclusions. So the high definition gamma ray, it highlights expected sedimentary features, such as channel sands that are not apparent in the seismic data. The outcome of dry hole is confirmed by the gamma rays result. And then two very important things here are, you must be aggressive with the removal of noise during conditioning. So I can't emphasize that enough, because I did comparisons with, I would say, strong conditioning parameters, and then weak conditioning parameters, and then no conditioning. And I come to the conclusion, of course, there is too much conditioning, but you must be aggressive with the removal of the noise. And then last, and as a geophysicist, I have to say this again, there was no well with logs available at the reservoir level for the second well. Therefore, it reduces confidence in the process. So you just have to say that. And this is not my first machine learning project for gamma ray. So I think it's extremely important to have that second well to use as a validation or a blind well. So in this situation, we didn't have it, but the sign that the well was, the correlation between the measured and the predicted was very high at the primary well. That gives confidence. But anyway, I just thought I'd mention that because I think it's extremely important. Acknowledgements. I'd like to thank Radiant for their permission to publish the work, Multiphysics for the support provided to do this presentation and this poster, and then DGB Earth Sciences for the software license. And that is it. Thank you very much for your time. Enjoy the rest of the conference.